Welcome to another video in numerical method for thermal engineering graduate programs. Once again, we are excited to get you on board in our online class at Wolaita University. Coming back to our course, we'll continue from our last session in linear algebra. As you may recall, we discussed about motivation of studying numerical method as engineers in the first video. In the second video, we start the linear algebraic concepts such as intermediate value theorem and Taylor series expansion, alongside their application in transforming and simplifying complex functions to a manageable polynomials. We illustrated how such transformation can be used in engineering contexts, because this is a straightforward process to derive and integrate polynomials than other forms of functions or equations. We care a lot about derivatives and integrations as engineers because our career is overwhelmed with solving problems using mathematical models with them regardless of our specialization. We also introduce algebraic expressions of linear system of equations in both vector and alternative matrix form. Each offers their own benefits. I found vector notation simpler in deriving insights from a given equation because individual coefficient and the coefficient multipliers and corresponding variables are written next to each other using vector form adjacent to each other, while I prefer matrix form for their versatile steps in finding roots and solutions. We started by looking into eigenvectors and eigenvalue theorems. We also solved numerous relevant problems in each of the above concepts, both numerically and graphically. In the latter of which, we also tried to look into illustrate their accuracies using multiple plots and graphs about various points of their estimation. So coming back to linear systems, that is today's first topic. Two techniques used in solution method. The first one, direct method, include Cramer's rule, Jordan's, or also known as Gauss-Jordan method, and the third one is Gauss elimination. Both direct and indirect use row elimination techniques similarly. Jordan continues until the coefficient matrix capital A transformed into identity matrix. Once identity is achieved, solution appear right. In example 2.4, given two flow equations, the first 2 plus 3 rho equals 8, and the second 4p plus 6 rho is 16 is given. Notice the second equation is just the product of constant 2 in this case and the first equation. By seeing, you can tell this equation has an endless pair of solutions. But for practicing Gauss elimination, first put the equation in matrix form. Capital AX equals P. The coefficient of P are 2 and 4 vertically aligned in the A, while those of rho 3 and 6 adjacently comes next aligning horizontally to the first array. Also note that the term vector is used when you refer a single value in matrix. Remember, single row or single column matrix, also called array. Don't confuse this vector with the one with the direction and magnitude in other contexts of engineering. Notice the next thing you see on the screen where the matrix A and the B array from left and the right hand side respectively appear or put next to one another separately by vertical bar, taking out variables. This notation is known as an augmented form of matrix. This helps you not to skip the operation in matrix A, maintaining the same manipulation you used for B as well. So Jordan step attempts transforming A to identity matrix. This literally means we carry out elementary row operation to set all other entries except the diagonal to 0. Then set the diagonal to unity, that is identity matrix. Guess why the first row is multiplied by the reciprocal of the first column entry of the first row. Since the entry in column 1 of row 1 is 2, multiplying the entire row in the augmented form by its reciprocal is to achieve unity in the first element. While keeping everything else other than row 1 intact. But subsequent operation on row 2 has the goal of achieving 0 in the first entry in row 2. Why? Because our target is achieving a value unity, that's 1 in here and here. There everything else is 0. That is called Jordan. What do you think should be done to make the first entry in row 2 to nil? Just by subtracting the product of constant 4 times every entries in row 1 from the row 2 gives you that. But you see, we arrived at the expected infinite pair of solution just by the second step using Gauss-Jordan. Gauss elimination, on the other hand, eliminates it stops after achieving triangular matrix. Please refer more examples in the reader, but I have to highlight you here that this triangular matrix can be upper or lower that entries in half part. Here is brought to 0 through elementary operation. Now see the last row where you have all other entries are 0 except negative 11. If you put the last row back into vector form, you will have minus 11 times z equals 12. Thus, the value of z is 11 over 2. See the second row as well. Now you have the value for the z from the previous calculation, and the only unknown in the second row is y. You substitute it to find y and proceed to the row 1 having values for y and z. Then using back substitution, back substituting y and z in the first row to solve for z, that is, it offers you, if the step here is Jordan, the manipulation would have continued until when? I hope you might have answer for that. So generally speaking, row elimination is multiplying and subtracting row or column inputs. Zeros out values above or below diagonal. Recall zeros below diagonal means upper triangle. Its opposite is lower triangular, often called LE. After triangular form, solve variables by back substitution as we did earlier. Start from last variable and move upward sequentially. This process is straightforward and I left the Cramer's rule here because we covered in stability analysis. There we calculated determinants for eigenvalues and found corresponding eigenvectors. Cramer's rule uses determinants to find solutions. It's direct and less practical for large systems. So we focus on elimination method. Of course, in the next session, the most enhanced one in iterative approach, which is also known as indirect approach. To save time for iterative methods later, I will skip other direct methods now, but you have solved examples in the reader. Iterative methods modify matrix transformation strategically. The aim is to arrive at diagonally dominant coefficient pieces strategically. Diagonal dominance means biggest absolute diagonal difference, regardless of its sign or whether it is negative or positive. This improves convergence and the solution stability. Jacobi and the Gauss-Seidel are common iterative methods using apparently similar formula in equation 7. This involves calculating the row entries using this formula or algorithm one by one, iteratively, meaning repeating the calculation. When you calculate i's row, say temperature entries in row I, the entire row is multiplied by reciprocal of the diagonal element AII. That's the diagonal element. Pardon me if I sound redundant, but also understand the context where not everyone is fluent with these matrix terms. Then breaking down the term inside bracket, you would use the backward substitution step of subtracting sum of products of the known values of our variable temperature A and their corresponding coefficient Aij from the value Bi. When doing this, you carry out all this calculation of other this calculation, that exceptional row I, while maintaining other rows. As you would see, the bottom index in the summation J is not equals to I, which means you skip that specific row under consideration for that calculation, but modify all other rows. This is called pivoting. This calculation continues until step K, where the results of calculation in case K plus I step are the same, which means your next calculation will have no impact because the output no longer changes. We call this solution convergence. Similar to Gauss elimination, the iterative approach in equation such as 7 and 8 of iterative approach takes ground in backward substitution, where you proceed from the known values to the unknown, from last to first row. See the example 2.4. Jacobi uses reverse iteration or initial regress. It updates all variables simultaneously in each step. Gauss-Seidel stores recent values. It updates variables sequentially and improves efficiency. Consider 2.5 for Gauss-Seidel. You have discretization formula of equation. Of course, you will see this concept in another chapter where you have numerical differentiation as well as ordinary differential equation in the last chapter. Don't emphasize on the equation where the equation came from, but on the way used to solve the equation itself. So solution method, I advise you to leave your concerns of the origin of discretization for future session. So the first I is when I equals 1 and I minus 1 is 0 because I is 1 and I plus 1 is 2. When you substitute this these and the values of known temperature T1, which is, T naught, which is 200 in discretization equation of conductivity transfer equation, you achieve equation A. Repeating this step for I equals to 2, which is case 2, gives us equation B. Substituting once again for I equals 3, the known value of T, which is 400, given with our problem specification. When we put equation A and B and C, it gives us linear systems of algebraic equation. From here, let us use Gauss-Seidel, taking an initial guess at the interior temperature T1 equals 150. We simultaneously solve first or compute T1 in equation C, or you can start also from equation A. Use its results T1 and substitute in equation B to estimate T2. Then use the result of both our initial temperatures, T1 and the T2, to estimate T3 in equation 3. In equation B. We then go back to equation A and repeat the process until the results of our calculation no longer varies. Had this been Jacobi, we could have simultaneously solved both equation A, B, C independently, taking all interior temperatures T1, T2, and T3 150, calculating for T1, T2, T3 in equation A, B, C, taking the initial guess, all our initial assumptions for all interior T's 150. Therefore, both Gauss-Seidel and Jacobi use backward substitution, but during Jacobi iteration, the result of entire matrix updated at step K. Then the process starts all over again, while Gauss-Seidel continuously stores and updates every row elements or entries. This makes Gauss-Seidel faster than Jacobi. Therefore, formula looks similar, but their updating timing differs. Many references you might lack clarity or it might confuse to get a combined accelerations of using direct or indirect method, but I hope this video clarifies concepts and comparison. Save it for future reference and review. See table 1 for efficiency comparison details. Gauss-Seidel is efficient but not foolproof. But if your equation has numerous equally bigger entries, say row 3 has entry -5 in column 1 and column 5, the same value 5, but +1 in column 4, but everywhere else, which means the value in the coefficient matrix, the column entries in that row is less than 5. Since the absolute value of both -5 and +5 are equal, you can't arrive at diagonally dominant matrix. In this case, look for other methods than to solve. Try swapping rows for columns, one at a time. Never swap rows and columns simultaneously. Aim to maximize diagonal entries, absolute values. This helps achieve diagonal dominance effectively. Then iterative method can converge reliably and quickly. See comparison in table 1 for more clear picture and solved problems for skipped bar, because I assume these are a bit amazing. You may give a try yourselves. Now, let's proceed to nonlinear equation. Unlike linear systems with a polynomial of order 1 each, nonlinear equations are polynomials with order greater than or equal to 2, or other form of equation like rational function or so on and so forth. While there are also strategies of solving nonlinear equations, solution techniques applicable for both linear and nonlinear systems. These include Newton-Raphson, named after its first and users, false position method, and so on. So recall that all equation examples we saw so far are the unity for one order. That's why we for the just remember the slot equation y equals mx is a hint. Now you might have a clue about nonlinear equation. Simple equation above, which is nonlinear. It is Boltzmann law, which involves terms of temperature for number of force, order, or degree. Therefore, see Newton-Raphson's method finding solution for roots between rings or known values and successive iteration are now having initial guess, where our new computation is the difference of ratio of function to its derivative evaluated at our previous evaluation, initial guess, and the previous case. False position appears similar to it. Accelerates convergence by multiplying the ratio of the Newton-Raphson equation with some weight. Other method of solving nonlinear equation are using graphical. See what it is. To sum up, we model Bernoulli equation, solve them numerically using different techniques. That's what we have for today. The next session will begin evaluation of definite integral and differential. Take care.